everyone. This semester, my group and I decided that we wanted to learn more about Grover's algorithm in quantum computing. However, before we talk about Grover's algorithm and how it helps us retrieve any unsorted data, let's go over how classical computers do so. In classical computers, we transform any and all data into zeros and ones, and these are called bits. Notice how in quantum computing they're called qubits, but in classical computing they're called bits. These go from high voltage to low voltage for processing, and then they pass through a series of gates called logic gates, which can manipulate the data to figure out the result that we want. Logic gates are like AND gates, OR gates, NOT gates, XOR gates, basically anything that you would learn in CMSE 250 or discrete structures. And this can be arranged in different ways to process the bits and produce the output that you want. This may seem like the process works really well, classical computing as it is, but if you think about it, it really won't help you solve problems that are at an exponential complexity. And in order for us to reach the full potential of human knowledge and keep on discovering and keep on going, we need quantum computing to be able to learn and solve these big problems that classical computers simply cannot solve.
Hi, I'm Nikita, and I will be talking about how quantum computers retrieve unsorted data, which is by employing an algorithm called Grover's algorithm that was devised by Love Grover in 1996. So let's say we've been given this unsorted database, and we're trying to find the omega value, which is highlighted in red. With n elements in the database, the Grover's algorithm can actually find the omega value in O of square root of n evaluations, which just means that it requires a square root of n number of operations to find that value. This is significantly less than classical computers, which require n operations to find that value. Now, more about the algorithm itself. Grover's algorithm employs two oracles, which are black box operations. This just means that the operator is unaware of what's happening within the oracle or the system. And these oracles essentially get queries passed into them, and they return some sort of answer.
So I'll be talking about Grover's algorithm's procedure. The first step is to initialize two 4-bit registers, and the first one is a quantum register and the other one is the classical register. After that, you create a circuit and apply the Hadamard gate to all qubits in the circuit. What the Hadamard gate does is that it puts all qubits into superposition of 1 or 0, so they're equal in probability, and this is shown by the picture here that all qubits are in superposition because they're equal in probability. And before I go any further, note that W is our expected value, and that's the value we're searching for in this search algorithm. The gray areas or the gray qubits are things that we don't really care about. After the qubits are in superposition, we can create an oracle, and an oracle is essentially a black box that passes in queries. And what it does is that it inverts amplitude. So on the next slide, you can see here that W is inverted, and this is only done to our expected value, which is W in this case, and everything else stays the same.
Hi, and my name is Lee, and I'll continue to introduce the following steps of the Grover algorithm. And after the first three steps Rita have introduced, then the following things are not that difficult. So for step 4, we mainly introduce this diffuser to reflect all the amplitudes across the average amplitude line, like the right figure shows. And that action will make our target state have the highest amplitude, and while other states will become lower amplitude. And then the following steps are much more easier. We can just compute the oracle and diffuser steps, like repeated square root of n times, where the n is the number of states. So in this step, the possibility to find the target state will increase to a very high root, so we can easily find the target states among the other states. And then here is the last step of the Grover algorithm, that is just to run the simulation on the qubit quantum circuit. So it's not really difficult, right?
Hello, my name is Naaman Trumbull. To conclude our explanation of Grover's algorithm, let's look at the exciting future that quantum computers have. Did you know that in 2019, Google published a supremacy claim where they asserted that quantum computing was going to be the future of computing? If Google, one of the largest technology companies, says this, you know that it's serious. Recently, in 2022, IBM unveiled a 433 qubit quantum computer that is promised to eventually be able to perform processes with greater speed and efficiency than any classical computer that came before it. If you tried to apply Grover's algorithm to this computer, you could search through this many data points. Imagine moving this decimal point 130 spaces to the right. That's a lot of data. And that number would only increase exponentially as we add in more qubits. Researchers are making historical strides in quantum computing, and before we know it, they could take over classical computers.